Okay, so again, officially welcome to the final event of InteGradeDH project. It is a project, as most of you know, funded by IHC platform within Annex 14, with a focus on the large-scale integration of low-grade sources into district heating with geothermal seasonal storage, and that, of course, requires heat pumps. So three partners were in the project. Europe Research as coordinators, Hawk University with Professor Stefan Holler and Dmitry Romanov, and Christina Lignerud, who is also professor at Lund University, but she participated in the project as private consultant. Unfortunately, she was not able to join today, but I will briefly present her results as well. So a couple of words of introduction about the project context and the main motivations behind it. Later on, we will have sessions managed by my colleague Amir Jodairi, giving an introduction about the methodology, then Dimitri about the case study of Göttingen, and Amir again about the case study of Bolzano. But yeah, in terms of context, of course, the rationale behind the project is about the decarbonization of district heating networks with their need to identify transition pathways from fossil fuels towards more sustainable sources. It is widely recognized that waste heat offers large opportunities in this direction. It is not always so easy to identify sustainable sources. Waste heat at the same time is largely available at low temperature, which requires heat pumps, and also makes the integration within conventional networks at high temperature not so easy. So there is an implementation gap from this point of view. The temperature of waste heat, the fact that waste heat is largely available in summer, a period where district heating demand is, of course, lower. And a potential answer to this mismatch is offered by seasonal storages, which have already been proposed in the past, but with several existing issues. So pit thermal energy storages, aquifer thermal energy storages, and shallow borehole thermal energy storages have been explored, but all with issues partly related to space occupation, partly related to costs, and partly related also to permitting aspects. Within the InteGradeDH project, our idea was to focus on low-grade waste heat because of its large availability, and to tackle medium-deep borehole thermal energy storages, where medium-deep means about 1 kilometer of depth. This can solve, in some cases, the space occupation issues and also some permitting issues in some areas for shallow bits, as we will mention later. In terms of, let's say, steps of the project, which will also be reflected by today's agenda, of course, we needed to develop a methodological framework, and in the end, the project offers this kind of framework as one of its main results. This framework was applied to case studies to offer some practical information. The outcome was not anyway a full design, and the network was mainly used to provide the heat demand and to ensure energy balances without entering into detailed analysis. And as a final step, also implementations aspects and more, let's say, business models aspects or risk aspects were considered. So the first point we will present today is indeed the modeling and integration framework. It's more at the planning level. It will anyway have to take into account operating schemes and performance indicators with these two key ingredients of low temperature waste heat and medium deep borehole thermal energy storages. You will see that heat pumps, of course, also play a crucial role to manage the temperature differences with the network. Case studies which will be presented are Göttingen and Bolzano. The topic as such was, let's say, the subject of a call for proposal of IADHC, but it is quite relevant for these case studies. In the case of Göttingen, for example, where there is a local network, the university campus, which is quite extended. There is also a data center facility there with a large amount of waste heat, with also interesting temperatures because of a mixing of air cooling and liquid cooling. So making this exploitation and the interest of seasonal storage quite relevant. For the Bolzano case also, we have a large availability of waste heat. There is also a big waste to energy plant, which also makes the case of high temperature, excess heat. And even if not directly planned at the beginning of the project, we included this analysis as well to offer also an additional comparison to the low temperature case, which is pretty relevant for Bolzano. The case of Bolzano is also interesting for these medium deep applications because in the Bolzano area, there are strong limitations for shallow beaches. So shallow boreholes are basically prohibited in most part of the city because of hydrological conditions. Going for medium deep applications would allow to stay at the boundary of this area and also would follow a completely different permitting process. Of course, as you will see, cost issues are there, but we will discuss it later. So at the end, we will briefly review also general risks, business models, and just a few comments on pricing considerations, going towards the final remarks, and then questions and answers will be started. So with this, my introduction is done. I'll now give the word to my colleague Amir Jederi, focusing first on the modeling framework. So please, Amir.
Hi, good morning, everyone. I'm Amir from UREC Research, and I'm going to talk about modeling framework with a focus on integrated assessment of waste heat, medium deep beaches, MD beaches, and heat pumps, together with common modeling assumptions and performance indicators for the case studies. So I will first introduce the logic used in the project. So waste heat recovery in district heating is not only about the annual heat potential. The useful contribution depends on the interaction between source temperature, seasonal demand, storage behavior, heat pump operation, and cost. So there are two technical mismatches generally mentioned in the literature. The first is the temporal. Waste heat can be available rather continuously, while district heating demand is seasonal. So seasonal storage, and with the specific case of our project, BTES and MD BTES, to be more specific, is relevant. The second mismatch is the temperature mismatch. And for this, waste heat or recovered BTES heat may be below the district heating temperature, so heat pumps are needed for temperature upgrading, thermal upgrading. So these technical solutions introduce an economic constraint: drilling capex, heat pump investment, electricity use, and operation and maintenance costs, as I mentioned here. So these three pillars are coupled and cannot be assessed independently. Heat pump capacity affects BTES temperature, BTES extraction, and electricity demand. BTES size affects thermal stability and drilling cost. And district heating temperature affects the temperature left by the heat pump, accordingly COP, and levelized cost of heat. To address these challenges, we developed an integrated framework that simulates the hourly energy flows, verifies multi-year BTES heat pump as a subsystem feasibility, and converts the resulting heat delivery, electricity use, and investment needs into a set of techno-economic indicators. So this slide shows the generic system concept used in the project. It defines the possible thermal pathways between the waste heat source, the BTES, heat pumps, and the district heating network. There are three main pathways, as you see here, pathway groups. First, direct use. When the waste temperature is sufficient, it can supply the district heating network directly, as you see here in this way, or charge the B test directly. Second is the heat pump assisted integration. When the temperature is too low, the heat pump upgrades either the waste heat or the recovered B test heat. Third is the seasonal shifting. As you see here, we have BTS. Surplus heat is stored in the BTS during low demand periods and is recovered later for district heating usage. So the scheme is not a fixed operating mode. It's a map of possible pathways, and the active pathway depends on the hourly demand, waste heat availability, and temperature conditions. In the following slides, I will focus separately on the MDB test response model of the borehole, field, the heat pump model, and the assessment indicators we consider for the study. So the MDB test module receives the hourly charge-discharge signals from the system operation. In charging periods, this is the waste heat which is injected into the bore field. In discharge periods, bore field acts as low temperature source for the heat pump. So the storage model is represented as a coaxial medium deep borehole heat exchanger using a G-function based thermal response approach. For this application, for the sake of our project, we modified the original PyG function that is available as open source to use the inlet temperature and mass flow rate as the boundary conditions rather than thermal power as an input, which is the case for the original PyG function. This modification better reflects the waste heat charging where the waste heat source temperature and mass flow rate is imposed, and the exchange heat with the B test is calculated by the model itself. So the main inputs are the bore field layout, depth and spacing, effective ground properties, and ground temperature as well, together with mass flow rate and inlet temperature. So the model calculates the outlet fluid temperature, injected and extracted heat, and long-term thermal drift of the ground. So these outputs are then used in sizing procedure, as you see here, which is the stepwise. And first, charging feasibility verifies that the bore field can absorb the waste heat efficiently, while hydraulic feasibility checks that the assumed flow rates remain within an acceptable range. And then during discharge, the MDB test inlet temperature must stay above 0 degrees C to avoid excessive ground cooling. And finally, the 25-year simulation verifies that the repeated seasonal cycling does not cause progressive ground thermal drift. So this MDB test module identifies planning level bore field configurations that are thermally feasible when it is coupled to the waste heat and heat pump. So the next is the heat pump model, and it's coupling to the MDB test and district heating. As you see here, the heat pump connects the low temperature side of the system to the required district heating supply temperature. On the evaporator side, the source can be waste heat or heat recovered from the MDB test. And on the condenser side, the target is the district heating supply temperature requirement. From these two temperatures, the model calculates hourly COP, heat pump electricity use, useful heat delivered to the network, and seasonal performance factor SPF. To be more specific, heat pump is the COP is calculated using a simplified Carnot-based relation with the pinch temperature difference and a lumped efficiency factor. the important point is the coupling. Lower source temperature or higher district heating supply temperature means higher temperature lift and lower COP. So the heat pump capacity should be a part of sizing procedure. Obviously, a larger heat pump is not automatically better because it can extract more heat from the MDB test and may violate the minimum temperature constrained by the B test. Therefore, heat pump output is constrained by residual district heating demand, heat pump capacity itself, and the MDB test temperature constraint. The last step of this modeling section that I would like to present is then to convert the technical outputs of the MDB test and technical outputs of the heat pump model into performance indicators that are used commonly within the case studies. So this slide closes the model section by defining the assessment basis used for the case studies. As mentioned earlier, the modeling framework uses a planning level boundary, and it is pointed out by Marco. So it is detailed enough to compare integration pathways and identify the main technical and economic drivers, but it's not a substitute for project level engineering design. So the district heating system is represented through aggregate hourly demand. Waste heat is prescribed, so detailed waste heat source dispatch and part load operation are not explicitly resolved. Direct waste heat use and storage units operation are represented through a rule-based dispatch logic. And the MDB test, medium deep borehole thermal energy storage, uses a coaxial bore field response with the effective ground properties. And the heat pump uses a simplified Carnot-based COP representation. And finally, the economic assessment is performed at the subsystem level. So full project level costs are outside the boundary. So within this boundary, configurations are compared using common indicators. The technical indicators are shown in this table: useful heat supply, residual demand coverage, cumulative unmet energy, MDB test inlet temperature constraint, and the long-term drift of the MDB test itself, seasonal performance factor, and electricity use. And the economic indicators includes capex, opex, levelized cost of heat, net present value, internal rate of return, and discounted payback period. Of course, the LCOH is the main cost indicator and compares discounted lifetime with the discounted useful heat delivered. And this, so the overall, let's say, indicators gives a common basis for interpreting the case study results. Based on this common framework, the presentation now moves to the two case studies. Dimitri, our colleague, will first present the Göttingen case study. Then I will return to the Bolzano application. Dimitri, floor's yours.
Yeah, thank you, Amir. Yeah, so I'm Dimitri Romanov from the Hawk University. I'm going to focus on the case study of Göttingen, on the shallow and medium deep borehole storage options for the data center waste heat in campus. I'm just trying to find the laser pointer. Yeah. Right. So this is the map of the North Campus in Göttingen, or the map of the Göttingen, where you see the North Campus. We have around 40 buildings there belonging to different research organizations, and those buildings were built mainly in 1970s. So the total heat demand of the area is about 40 gigawatt hours, which causes around 11,000 tons of CO2 emissions per year, because the energy supply there is gas-based. So we have several CHP units consuming gas, burning gas. One big CHP unit with 60 megawatts of thermal output, and 3 small units. Yeah, but also there are some, yeah, as we already mentioned, there is a data center, and also there are cooling machines, and there are yeah, sewage systems. All of these potential waste heat sources can be exploited. And in this work, we focused mainly on the data center. And we received the data from the data center operator. These data are shown in this figure or in this slide. On the left-hand side, you see the electric load of the IT equipment of the data center, which we assumed to be available waste heat for our analysis. Here you see the air-cooled. So yeah, there are 2 rooms, air-cooled room and liquid-cooled room. Both, yeah, generating waste heat, and the brown curve is representing the total available waste heat, and the median value is around 0.8 megawatts. On the right-hand side, you see the outdoor temperatures and the primary return temperature in the cooling circuit, and this temperature was assumed to be the waste heat temperature with the median value about 30 centigrades. We considered several scenarios how we can recover waste heat from the data center, but the very first scenario is business as usual, to be compared with the waste heat recovery scenario. In this business as usual scenario, we have district heating system supplied by natural gas, and we have modular data center which emits waste heat in the atmosphere. So these systems are not connected. In the next scenario, waste heat recovery scenario, we use the waste heat from the data center and upgrade it via the heat pump to provide it to the district heating system, and thus replace some part of the fossil fuel used. And in the third scenario, you can see here 2 operation modes. Yeah, the third scenario is basically the extension of the second scenario, where we additionally consider the shallow borehole thermal energy storage. And here you see 2 operation modes. For example, in summer, we charge the storage with the unused waste heat from the data center. And in winter, we discharge the storage via the ground source heat pump, and thus we provide heat to the district heating system. For the simulation, we assumed these initial parameters. So we assumed 150 boreholes, each of them 140 meters deep. The bore field, the size of the bore field is 70 meters by 45 meters. We consider W tubes, and the mass flow rate is 0.4 liters per second per borehole. We consider different district heating design temperatures. The existing network has high temperature, 100 up to 120 degrees, and we considered additionally 3 potential future scenarios where the district heating system is the temperature is reduced in the district heating temperature. And yeah, these economic parameters were considered for the economic evaluations. The results of those simulations are summarized in this table. So from the economic perspective, if we consider levelized cost of heat, the waste heat recovery scenario is the most promising scenario. It has lower levelized cost of heats than the other 2 scenarios, and it allows us to supply the campus with, let's say, from 6 to 8 gigawatt hours per year a part of what business as usual scenario can provide. It requires additional electricity, and it allows us to save around 1,300 tons of CO2 per year. Waste heat plus storage scenario can be economically better than the business as usual scenario in some cases, but it's still worse than the waste heat recovery scenario. And however, here in this scenario, we can provide a bit more heat to the campus simply because we store some of the waste heat and then provide it additionally in winter. For that, we also need more electricity to run the heat pumps, and yeah, it allows us to reduce CO2 to have higher CO2 reductions up to 1,600, 1,700 tons per year. And then the next question was, so the storage scenario was not so promising compared to the scenario without the storage, so heat recovery storage without heat recovery scenario without the storage. And in this sensitivity analysis, the idea was to find out some scenarios, some parameters where borehole thermal energy storage, shallow borehole thermal energy storage could be feasible, economically feasible, or performing better than simply recovering waste heat. And this sensitivity analysis showed that the specific cost of the storage should be significantly reduced, also together with a significant decrease of the electricity price, and at the same time the heating price should be higher. So the electricity price should be lower, the storage cost should also be lower, while the heating price should be higher so that the heat is more valuable. After performing this analysis, the next focus was on the medium deep storages, medium deep borehole thermal energy storages, and the idea was to consider multiple parameters, multiple potential configurations of those borehole storages. As you can see here, the depth from 400 to 1,000 meters were considered. The bore field consisting of 4 to 64 boreholes was considered. And at the same time, different waste heat temperatures were also considered from 30 to 90 degrees. And the district heating temperatures were as in the analysis before. So here you see the charging, the scheme for the charging mode, where we have a heat exchanger, and the scheme for the discharging mode, where we use heat pump to upgrade the heat from the boreholes to be used further in the district heating system. The methodology of this work for the medium deep borehole thermal energy storage is summarized here. So some of the things were already mentioned by Amir. For example, we use the method that we validated before. The method includes the pi-g function with effective undisturbed ground temperature and thermophysical properties. We used a simplified Carnot-based performance model for heat pumps. And for the economic evaluations, we used the concept of break-even costs. So it basically means that if we exceed these costs, then the storage is not economically feasible. And how we calculated these costs: we take the formula for net present value and we set it to 0. And from this formula, we found the initial capex required for the whole system. And from this initial total capex, we subtracted the capex for the all other components except for the storage. And that's how we got this specific break-even specific medium deep storage cost, euros per meter.
Very short interruption from my side, Dimitri. So I invite again the people online to write questions in the chat. There will be not the time, of course, to describe in detail all the aspects contained in the slides, but we will be glad to answer your questions at the end or even later. Please, Dimitri.
Yeah, thank you for the reminder. Right, so here I'm showing the results of the simulations. First, I show here the heat delivery for the bore field of 8 boreholes by 8 boreholes, so 64 boreholes in total. And here you see different waste heat temperatures, different district heating temperatures, and different depths. So the values range or change in a wide range from 5.5 gigawatt hours per year to almost 31 gigawatt hours per year. And for the case study in Göttingen that we considered previously, where we have 120 degree district heating temperature, district heating system, and 30 degree waste heat source, so the data center, the values would range from 6 to 16 gigawatt hours per year that we could potentially deliver to the campus using this bore field of 64 boreholes. And as for the break-even specific costs, you can see the heat map here. The values are relatively small compared to the actual drilling costs. So they range from approximately 55 to 313 euros per meter, which is, as mentioned before, not so high. And it would be beneficial, to have these high break-even costs, because if you exceed them, then the project is not feasible. And for the Göttingen case study that we considered, the values are, they range from 55 to 58 euros per meter. That would be too low for such system in Göttingen. And the sensitivity analysis for this part was done using Monte Carlo method. And here you see the results of the Monte Carlo simulations done for different distributions of heat price, electricity price, and the discount rates. Maximum values shown here are 500 euros per meter, which could also be challenging for a economically feasible medium deep borehole thermal energy storage. And in some cases it could be close to zero or even below zero, these costs. So these were the results of the medium deep storage simulations. And I think now I give the word back to Amir.
Thank you very much, Dimitri. Now I'm going to talk about the Bolzano case study with the focus on high temperature waste heat and low temperature waste heat that I talked about in the existing urban district heating system, together with technical performance, LCOH, and break-even conditions, but with regards to Bolzano, not compared to the Göttingen. So Bolzano district heating is an existing urban district heating system which is supplied by a mix of energy sources. One of them is the high temperature waste heat from waste to energy plant with 30 megawatt thermal and at the temperature of 70 to 95, which is compatible with direct district heating integration. The DH system already has a large tank thermal energy storage, TTS, with a capacity of 210 megawatt hour thermal. And for the planning horizon, we use the 2035 DH scenario. Future scenario for 2035 to represent the expected demand densification and next network expansion. Based on the power plot that you see here, the annual heat supply is around 330 gigawatt hour thermal per year. And the supply temperature is around, the current supply temperature is around 70 degrees C in summer and 95 degrees C in winter, with a return temperature of 55 degrees C, which would be held for the 2035 scenario as well. So although the district heating system of Bolzano is classified as an efficient district heating within Italian framework, further decarbonization is required. And here the question is that how additional waste heat recovery and seasonal storage could be integrated into the current system. So that's why we considered another waste heat source. The other waste heat source is the low temperature waste heat source, which is considered for this project, and is the waste heat from a dairy facility represented as 2.5 megawatt thermal at around 30 degrees C. And for the seasonal storage, we considered a bore field of 1,000 meter MDB test with an effective undisturbed ground temperature of 26.5 degrees C. So the two mentioned waste sources differ by temperature level, and this leads to two different integration pathways that I'm going to talk about in the next slide. So the temperature level of each waste stream determines whether it can be used directly or first upgraded, should be upgraded by a heat pump. For the high temperature waste heat that you see on the left side, in summer, waste heat can be injected into the can supply the district heating through tank thermal energy storage, as you see here. And in winter, so the surplus during summertime can be injected into the BTES directly without any heat pump. So in winter, high temperature waste heat still contributes, as you see here, directly to through the TTES, tank thermal energy storage, but it's not enough to cover the residual demand. So the stored heat in the BTES is recovered and upgraded by a heat pump before delivery to the district heating network. So for the low temperature waste heat pathway in summer, the low district heating demand is already covered by the high temperature waste heat through tank thermal energy storage. So low temperature waste heat here is used only for seasonal storage through heat pump to upgrade. So in winter, high temperature waste heat, as you see here, and tank thermal energy storage remain the direct supply route. At the same time, low temperature waste heat contributes through heat pump 3 for direct heat district heating support, while heat pump 1 recover and upgrade the stored heat in the MDBTES. So as you understood, the high temperature waste heat allows direct use and direct storage charging, whereas low temperature waste heat requires heat pump upgrading for charging as well as winter use. So now I would like to start with the results for the high temperature waste heat pathway only. So since for both pathways, high temperature and low temperature pathway, waste to energy heat is first used directly through the TTES in the district heating system. This plot shows in black the residual winter demand after direct high temperature waste heat use compared with the heat supplied by the BTES heat pump subsystem shown in orange. So the sizing procedure, as explained earlier in the model section, resulted in in configuration with 224 boreholes with a heat pump capacity of around 18 megawatt electrical. As shown here in the plot, the subsystem provide a large seasonal contribution of around 76%, but it's not a peak covering unit. During periods with high load, as you see here, black curve, the output is capped by the heat pump capacity and the MDBTES, bore-field thermal temperature constraint. So concerning the long-term behavior of the BTES heat pump subsystem, the SPF of the heat pump increases slightly from 2.6 in year 1 to 2.7 in year 25. In line with this, so this is because of the waste heat injection into the BTES. That's why we didn't have thermal degradation. In line with this result, the minimum inlet temperature to the BTES also increases from 0 degrees C in year 1 to 3.5 degrees C in year 25, showing stable long-term thermal behavior. So the key message here is that high temperature waste heat integration results in substantial seasonal recovery, but with a limited and capped peak load coverage. With regards to low temperature waste heat pathway, here the dairy waste heat is, as I mentioned earlier, is around 30 degrees C, and it cannot be directly injected into the supply to the distributing network. The low temperature, therefore, the low temperature waste heat contribution comes from heat pump 3, as I mentioned in the previous section, upgrade the available dairy waste heat for direct winter support, while heat pump 1 recovers the heat stored in the MDBTES. So this configuration obtained from the configuration obtained from the sizing procedure is smaller than that of the high temperature waste heat case, with 42 boreholes and the sizes of heat pumps that you see here. The system supplies about 34 gigawatt hour per year, corresponding to 25% of the residual demand coverage. So the long-term behavior is stable, as you see here. The minimum MDBTES inlet temperature remains above 0 degrees C, and heat pump 1, the heat pump which is connected to the BTES, SPF stays around 2.6 over 25 years. So here the message is that low temperature waste heat pathway is technically stable, but its contribution to the district heating supply is rather supplementary. So after seeing the technical results, the question is whether these configurations that we talked about are economically attractive. So the economic assumption used for LCOH calculation are heat price threshold, electricity price, drilling cost, fixed O&M and discount rate, as well as project lifetime that you see here. In addition, the waste heat is assumed to have zero purchase cost, and these assumptions define the reference case behind the LCOH values you are going to see here. So the stacked bars here show the LCOH structure for the high temperature waste heat and the low temperature waste heat pathways, split into the MDBTES and heat pump investments, electricity use, and as well as fixed O&M. So the table gives the investment basis behind the result that you see in the stack bar. So for the high temperature waste heat, the LCOH is 240 euro per megawatt hour thermal. This is mainly driven by the very large bore field. The total capex of the same pathway is around 200 million euros, and around 168 million euros of that is drilling capex, and the rest for the heat pump investment. And for the low temperature waste heat pathway, the capex is much lower, around 40 million euros, because the bore field and heat pump capacities are smaller. The LCOH is therefore lower, around 184 euro per megawatt hour thermal, but it's still above the threshold that I mentioned earlier. So although the low temperature waste heat system consumes less electricity in absolute terms, it delivers much less useful heat and has a lower system level SPF. Therefore, if you compare this purple part of the LCOH structure, therefore electricity use per megawatt hour of useful heat is higher, and the electricity becomes a larger share of the low temperature waste heat LCOH compared to the high temperature waste heat pathway. So overall, the key message and the takeaway here is that the economic challenge is not about the waste heat cost itself, but the infrastructure and electricity needed to store, upgrade, and deliver useful heat at the required temperature, district heating temperature matters. So after the LCOH structure, the next question is which parameters have the strongest influence on the economics of the low temperature waste heat pathway? I'm talking about low temperature waste heat because it was the scope of the project. And that's why from now on, I focus on LTW, low temperature waste heat. So the tornado diagram presents a one at a time sensitivity analysis. In this diagram, each bar shows the change in LCOH when one parameter is varied within its tested range, while others remain fixed. So the dominant driver of the LCOH is, as based on the analysis, is the drilling cost, because MDB test, as I mentioned, is capital intensive, and drilling represents the largest upfront cost. The next are the fixed O&M, discount rate, and electricity price. Fixed O&M, operation and maintenance, and discount rate matter because of the high capital intensity. O&M is somehow related to the capex, and electricity price also matters because low temperature waste heat delivery strongly depends on the heat pump operation. Among technical parameters, heat pump efficiency factor is the most relevant parameter because it affects COP and electricity use. And as you see here in this column, the ground parameters have a smaller influence within the tested ranges. So the takeaway is that low temperature waste heat feasibility mainly depends on the lower drilling cost, lower operation and maintenance, favorable financing and electricity conditions. And but there is one question still remain, and in the next slide, I will show which combination of these parameters that I mentioned can reach the assumed heat price threshold. So we finally look at the break-even conditions for the low temperature waste heat pathway using 100 euro per megawatt hour thermal as the heat price threshold. So in the first step, we considered 50% capex support. This reduces the LCOH from 184 to this value, but still remains above the threshold. In the second step, we combine the same capex support with a lower electricity price of 100 euro per megawatt hour electrical. And this reduces further the LCOH, but still does not reach the break-even value, which is 100 euro per megawatt hour electricity, thermal. Sorry. So then in the next step, we considered further frontier analysis, and the frontier plot, which is shown here, shows the combination of drilling cost and the electricity price under different operation and maintenance, as well as discount rate assumptions. Each frontier curve, as I showed here, represents combination of the so each frontier, is the LCOH value of 100 euro per megawatt hour thermal. Points below and to the left of the curve, each curve corresponds to a favorable conditions. So this plot is represented by 3 points, A, B, and C. Point A keeps the reference drilling and electricity prices with 50% capex support, favorable operation and maintenance and discount rate assumption, but still it is above the threshold. Point B keeps the reference drilling cost, but reaches the break-even with a lower electricity price, and also operation and maintenance cost of 1.5% of the capex, as well as discount rate of 4%. And finally, point C keeps the reference electricity price, but reaches the break-even with a lower drilling cost and the same favorable operation and maintenance and discount rate shown here. So here, the message is that capex support alone is not enough. Break-even condition requires capex support plus improvement in at least one major cost driver, which could be either drilling costs or electricity prices, under favorable operation and maintenance and financing assumptions. So sorry for being longer than expected. Marco, over to you.
Thank you a lot, Amir. I think this part of the parametric analysis is crucial to make understandable also the feasibility thresholds for these projects. I will conclude very quickly with a few slides ranging from risks to business models and pricing, which again highlights the work done by Cristina Lignerud. As I said at the beginning, I'll be very quick, but you'll find more information on this in the final report, which will be made public soon on the IADHC website. So concerning risk analysis, we followed a process in a few steps, starting with some general analysis about risk exposure for the considered technologies. Then this general analysis was conceptually tested on case studies. This allowed the identification of additional risks, and then we arrived to some quantification, of course, still with qualitative aspects according to a risk priority matrix, as you see in the slide. Just to exemplify a few risks, of course, many risks can be involved in this type of projects, also because of the novelty of some concepts. They can be classified also depending on the project phase. So some risks are related to the planning phase, other to the operational phase. Here I highlight just a few, let's say, major ones. We have heat pumps, so electricity prices, as highlighted by Amir, play a major role. So fluctuations or uncertainties in these costs can be important risk for the future. Waste heat is there, so this is a general problem with waste heat. Ensuring long-term availability is crucial. The cases tackled here are less problematic in this respect. So a waste-to-energy plant is expected to already have, for example, a relationship with the Bolzano district heating. Also, the campus, of course, has full control of the data center, but in general, this risk is here. BTES involves a significant uncertainty, so there are studies done in different ways to approximate the ground behavior, but of course, until an exploratory drilling is made, it's very difficult to have conclusive value. So for these large projects, some testing approach would be crucial. This system complexity is a risk by itself, which would of course come up in operational issues. And then planning a district heating system, of course, involves other sources. Many other risks could be imagined. They can be managed in different ways and mitigated in different ways. A few ones can be managed just in the planning phases and give rise also to go no go decisions. I also mention legal aspects and permitting aspects, which, for example, are quite relevant for the Bolzano case. But of course, again, this is something which can be dealt at the beginning of the project. Again, you will find more on this in the report. Business models were also considered in terms of understanding also ownership boundaries, relationships, especially between the waste heat owner and the district heating company, with approaches possibly related to prosumer concepts, possibly related to the servification of some aspects, like enhancing, for example, the let's say arrangement of district heating of waste heat recovery contracts, like cooling services. And this is also related to the final comment I would like to make about pricing in these kind of projects where the investment part is so high. It's very recommendable to have the tariffs split in two parts, a fixed part accounting for these large costs and a variable part. At the same time, what I mentioned before, so presenting waste heat as a cooling service can also help in building different pricing options. And finally, including flexibility, which these systems allow also in terms of operating temperatures and possibly inviting customers through tariff incentives to have lower return temperatures can be an important point. So with this, I come to the final remarks. It's a project involving many aspects, so many things could be pointed out. Here, there are just a few highlights on some things we also learned from this project. Again, I want to remark that our approach is at a planning level, so limited level of detail. Of course, in case studies, we showed the possibility to identify stable configurations, preserving the temperature of the ground on a longer term. But of course, it remains the big challenge of the economic viability. Even though with the parametric analysis shown by Amir, we have seen that it is possible to find some limiting configurations where this approach is feasible. Replicability and transferability of this approach mainly has to do with the framework. Then, of course, case-by-case analysis has to be done. And in terms of what are promising applications, of course, the reliability of waste heat supply, lower district heating temperature levels, and suitable soil conditions are, of course, crucial to get feasibility. Still, keeping in mind that drilling costs at the moment seem to be the main driver about the feasibility of this system, with also electricity playing a big role. Even though we analyzed the many configurations, this is definitely not the end of the story, also because of the level of detail. You have hopefully understood that we kind of large-scaled, so to say, the shallow BTES approach to a medium-deep approach towards these higher depths. In principle, also more complex geometries could be considered. We started from this point of view with a hard assumption, let's say checking challenging requirements, and then slightly improving the possible option. This point also has to do with more elaborated workfield configurations. In special conditions, it is also possible to go beyond closed loop configurations, as we considered here. If you have fractured ground or if you implement these solutions, then you can reduce the number of boreholes. But yeah, this was our limited assumption. And finally, we considered many costs, but of course, detailed design would include other items not included here. So I stop here. I also stop the recording. While I thank you, the presenters, for the interventions and for your participation.
I just reply to one.
And let's check if the recording is closed. And thank you again.